Welcome to the session. The following topics will be covered in this session: geometric tolerance zone, rules of GD&T, MMC, LMC and RFS, datum reference, the do's and don'ts for proper display in drawings, flatness. So geometric tolerance zone. So what is geometric tolerance zone? It is the second zone in the feature control frame. The first zone is for the geometric characteristic, which we have learned in the earlier session, the 14 geometric symbols, and the second one comes the geometric tolerance zone. So geometric tolerance zone, you can see as in the drawing below, it is the range, like the minimum to the maximum. So that is the geometric tolerance zone as shown in this figure. So it will be either a width or a diameter depending upon the place where it is being applied. So a diameter symbol will be preceded if it is a cylindrical tolerance zone. For example, if you look into this drawing, so it is given as straightness should be within a cylindrical tolerance zone of 0.1. So that is why a diameter symbol is given. If a diameter symbol is given, then it means it is for a cylindrical tolerance zone. So in the geometric tolerance zone, the value will be there. The value will be the value within which your geometric characteristic should be lying, and if it is having a diameter symbol before the value, then it means it's a cylindrical tolerance zone. If suppose if you don't have a diameter symbol, if a diameter symbol is missing, then it can be either between two parallel planes, two parallel straight lines, or two uniform boundaries as shown in this figure. In this figure you can see there is no diameter symbol shown in front of the geometric tolerance zone's value. There is a symbol given in the geometric characteristic. This symbol is for the symmetrical. So what it is trying to say is it should be symmetrical within a wide tolerance zone of 0.004 for this particular slot they are given. So this slot, it is straight. So what they are trying to say is this slot can be within a wide tolerance zone of 0.004 symmetrical with reference to A. So A is going to be the component face. So where they have made as the datum. So this is what we try to say. So when you have a dia symbol, then it is for a cylindrical tolerance zone. When the dia symbol is missing, this is for a wide tolerance zone. Now we are coming to the rules of GD&T. So there are three rules to be followed in GD&T. So these three rules are common for all industries like aviation industry, heavy equipment industry, automobile industry. Wherever you go, these three rules are common, as GD&T is commonly applied throughout any industry. It doesn't depend for any particular industry. Aerospace also they follow the same GD&T because GD&T is common for all the industry. So first rule states limits of size rule. Second rule is called as material condition rule, and third rule is called as pitch diameter rule. So we will see these three rules in detail. So first rule, limits of size rule. So what it says, the geometric form of a feature may vary so long as it stays within the limits of its tolerance. So what it is trying to say is, for example, if you look into the drawing, what it says is the magenta color boundary is the control zone, that is the geometric control zone. The smaller one is the lower control zone, bigger one is the upper limit of your size, that are called as the control zone. So your actual part can lie within this tolerance only. As per this drawing, if your profile, the black color profile is coming outside also as well as inside, so this kind of profile if you get means this component will not be accepted. Whereas if you see in the side view how we have given the lower limit of your size and the upper limit of your size, and the actual part is exactly lying within the tolerances, between the upper and lower tolerances, then it is correct. If you look into this drawing, the pink color part is the actual component, the orange color is your lower limit, and the transparent color is your upper limit. Your component is lying between the lower limit and upper limit, then this component is accepted. If you look into the below case, the pink color, it is lying above, outside the upper control limit. Lower control limit is here and upper control limit is here. Your component is not lying within your upper control and lower control limit. So this component will be rejected. So this is what the limit of size says. So what it actually means is whatever the size they have given in the drawing within the tolerance, if your component size actually when you measure physically, if it is lying within the tolerance, then this component is accepted. When it is going beyond or lying below the lower control limit or going above the upper control limit, then it's a rejected. So that's what the limit of size rule says. So rule number 2, very important rule, material condition rule. So what it says is on all applicable geometrical tolerances, a modifier must be specified whenever MMC or LMC are required. So MMC means maximum material condition and LMC means minimum material condition or the least material condition. That is the correct terminology to say. LMC is least material condition. RFS means regardless of feature size. It will be applied when there is no modifier is present. So how we will be using or how we'll be representing in the drawing is, for maximum material condition we use this symbol letter M, which is encircled inside a circle, and least material condition letter L enclosed within the circle. So if you find any symbols like this, L means it says least material condition. When you see a letter M within the circle, it says maximum material condition. So we will see what is maximum material condition and what is least material condition and how it is going to impact. So MMC and LMC. So if you look into this figure, so we can say for these features, and main important thing is the MMC and LMC will be applied for the feature of sizes only. So in this component, the features of size will be the slot. The 20 millimeter slot will be one feature of size, and 30 millimeter hole will be a feature of size, and your total thickness of the component 100 millimeter and total length of your component 100 millimeter will be a feature of size. So for example, how to find MMC and LMC, I will tell you. So first of all, what is MMC and what is LMC? As the name implies, maximum material condition, in the sense the component, the feature is produced at the maximum material condition, meaning it can be reworked and you can remove furthermore material and make sure that this component still lies in the tolerance zone. Least material condition means this is the worst case. After this you can't do any rework or you can't remove any material, and if you remove any material, this component will be rejected. So MMC means maximum material is there and it is within your tolerance limit. So you can do any rework and you can bring it within the tolerance also, and even then your component will be accepted. So that is what MMC and LMC says. So for whole features it will be slightly different, and for shaft or bar, pin, for those things it will be slightly different. So now we will find the MMC and the LMC for each and every feature. First we are going to find for the slot. So what is going to be the MMC and LMC for the slot? So slot, it is going to be like a whole feature only. So how we are going to find this one? The easy method is just you need to find what is the size of the slot. As per the given drawing, your size of the slot can be between 19.98 and 20.01. That we need to write it down. From this, you can say what will be the bigger size and what will be the smaller size. So the bigger size is 20.01 and smaller size is 19.98. Since it is a whole feature, maximum material condition will be the smaller size and least material condition will be the bigger size. So this is the easy way to detect the MMC and LMC values. So easy method is find the size of your slot or the whole feature, which is going to be varying as per the given drawing. Write it down, the lower to the maximum. The lower size will be the MMC and bigger size will be the LMC, meaning that MMC means 19.98. For example, in this component, after 19.98, if I am doing some rework, the slot is going to be rework in the sense I am going to remove some material. When I remove the material, your slot width will be increasing. When you remove some more material, instead of 19.98, it may become 19.99 or 20 or 20.01, but it can't go below 19.98. So when you are reworking, it can go up to 20.01. So that is what we say, it is maximum material. So 19.98, it is accepted. 19.98 is now also accepted since it is lying within the tolerance, but for some reason your flatness or straightness, something is going to miss and you are going to do some rework in the sense, then also you can do if your component is at maximum material condition, and then you can make this piece as accepted. Whereas in the least material condition, it is already with the minimum material, already it's 20.01 bigger size. If I try to remove any material to make any of your geometry characteristic to come within the tolerance, then this size will increase to 20.02 or 20.03, then this component will be rejected. So MMC is like a best condition, you can say, meaning that there is more material and there is a room for rework, and if you want to play anything, you can do it with the MMC. So for whole features, MMC will be the smaller size and LMC will be the bigger size of the feature as per the given tolerance. Now we will find the LMC and MMC for hole. So in this case, the hole diameter is 30 plus or minus 0.02. Same principle we are going to apply now. So what is the size your hole feature can vary? It can vary from 29.98 to 30.02 as per the dimension given in the drawing. So from this we can derive what will be the MMC. MMC, as I mentioned earlier, it is the smaller size, so it's going to be 29.98, and LMC will be the bigger size, it is going to be 30.02. Same concept like how we explained for the slot, we can do it for the hole also. This is for hole features. Now we will find the LMC and MMC for a opposite side, like not a hole, it is for a block. It is for a block or pin or for a cylinder or shaft, something like that. So you can find. So it will be in the opposite case. For example, what is the MMC and LMC for block? The block size is 100 millimeters. As per the drawing, 100 plus or minus 0.05. So you need to write down the minimum and maximum size between which this component can vary. The block thickness or block height can vary. So the size of the block can be varying between 99.95 millimeters to 100.05. So which means that the minimum size, if your component width is coming from 99.95 to 100.05 also, this component can be accepted. So in this case, when you can say it is maximum material condition is if it is bigger, meaning that I can remove material when your slot, or when the slot was a female feature, it's a whole feature, and this one is like a male feature. For these kind of features, when you remove the material, the size will be reducing. So when it is reducing also, the component need to be accepted. So in that scenario, 100.05 will become the maximum material condition of the block, meaning that when you have produced a component at 100.05 block width, you can rework it, you can grind it, or you can do some other operation, and if you reduce it, the size will come less than 100.05, but it will be above 99.95. So if it is between this range, then it is going to be accepted. So that is what MMC means, maximum material condition. So maximum material condition for a shaft or for a male feature will be bigger value as per the tolerance. LMC will be the least value as per the tolerance given here. So 99.95 is the least material condition. So after this, you can't remove material at all. If you are trying to remove any material, this component will be rejected since it is going beyond the tolerance limit. So these things will be applied as per the designer's view, like how he is going to use it for the assembly. Accordingly, he can apply. So when we need to specify anything in the drawing, you can use the, as I mentioned earlier, letter M within the circle for MMC and letter L for LMC. So we will look into one more figure for identifying LMC and MMC quickly, just a snapshot. So now I'm going to find the MMC and LMC for the center hole. The hole diameter is 8 plus or minus 0.002. So the size of the hole can vary between 7.998 to 8.002 as per the drawing. So as we discussed earlier, MMC for a whole feature will be the minimum size. So it is 7.998, and LMC for the whole feature will be the maximum size. It is 8.002. Similarly, we are going to find for the next feature, slot. So slot, again, it is a female feature or a whole feature, similar to a whole feature. So the size can vary between 6 to 6.001 as per the drawing, and MMC for the slot will be the minimum size, that is 6, and LMC for the whole slot will be maximum, that is 6.001. Now we will find for the OD, that is the block. The block is going to be the opposite feature of the hole. So we need to find carefully. So the size of the block can vary between 29.994 to 30.000. So in this case, the maximum material condition will be the maximum value of your block, and least material condition will be the minimum value of your block, that is 29.994. And when you consider the thickness, again thickness is like your block only, not like the whole feature. So we need to find it. It can vary as per the drawing, 12.581 to 12.583. Since it is like a male feature, the maximum material condition will be the bigger value, that is 12.583, and least material condition will be the least value, that is 12.581. So this is the way or easiest method to find the LMC and MMC of a feature as per the tolerance that is given in the drawing. And the third rule is pitch diameter rule. But how we are going to use this one is for the threads. If you are mentioning anything for the threads in the drawing, if it is given like this, just a feature control frame alone, which is having the geometric characteristic and your geometric tolerance zone and datum references, and if you don't write anything, then whatever you are telling, it applies for the pitch diameter. If you are giving the maximum material condition here, then it applies for the pitch diameter. If you want to mention anything for your major diameter of the thread or for the minor diameter of the thread, it needs to be written like this, major diameter or minor diameter. Like that, whatever you want, you can write it here. This is for threads. If we are applying for gears or splines or those kind of features, then we need to write even for the pitch diameter also. So if you want to mention anything, you need to mention. So whenever we are referring or whenever we are representing a gears or splines in the drawing with a feature control frame, you need to mention whether you are mentioning this one for the pitch diameter or for the minor diameter or for the major diameter. Those values needs to be written in the drawing. Whereas for the threads, for the normal thread like a ISO thread or UN threads, you need not have to mention if you are trying to represent it for the pitch diameter. You need to write only if you are mentioning for the major or for the minor diameter. So this is about the pitch diameter rule. Now modifiers. So again, we discussed earlier, that is the rule number 2. Maximum material condition and least material condition. So these are called as the modifiers. So these modifier can be applied to the geometric characteristics. What are the geometric characteristics? Is straightness, parallelism, squareness, angularity, position, concentricity and symmetricity. So these 7 geometric characteristics can have the maximum or maximum material condition or least material condition modifiers whenever it is being used in the drawing. For other geometric features, it is not at all applied. It can only refer to a feature of a size. That is the reason we are applying for the straightness, parallelism, squareness, angularity, positions, concentricity and symmetry. So only these features can have the modifiers. Modifiers are nothing but the maximum material condition and least material condition. When there is no maximum material condition symbol or least material condition symbol, means it is called as the regardless of feature size. So now we will see how the maximum material condition principle is going to play a major part in our geometric tolerances. So in this drawing, just I'll first explain this drawing and the symbol, what it says. So this symbol is applicable for the whole diameter 4.5 to 4 millimeters. What it says is perpendicularity of this hole with respect to A, the datum feature A, should be within 0.2 cylindrical tolerance zone at maximum material condition. That is M for maximum material condition, which means when this hole is at maximum material condition, it should be perpendicular within a geometrical tolerance zone, that is a cylindrical tolerance zone of 0.2 with reference to the datum phase A. So for this hole, what is the maximum and maximum material condition and least material condition? So maximum material condition is 4 and least material condition is 5. So when it is at 4 millimeters, the geometric tolerance, that is perpendicularity in this case, should be 0.2. So that is what it says as per the feature control frame. Whereas when your hole size varies from the maximum material condition towards the least material condition, the geometric tolerance value will also increase. How it is increasing is, for example, MMC is 4. When it is producing at 4.2, this 0.2 geometric tolerance will be increased with this 0.1 material which has been removed already. So the geometric tolerance will be 0.3. For example, when it is at least metal condition 4.5, the hole is bigger already, means that bigger in the sense it is at the maximum material has been removed. So it is at least material condition. Further material removal is not possible. At this condition, geometric tolerance as per the feature control frame it is 0.2, but the difference between the MMC and LMC is 0.5. When you add those two together, you will get a value of 0.7. So which means that at least material condition, the perpendicularity of the hole can be up to 0.7. So this will be useful mainly when you are checking this component, when this component is getting checked by the quality inspector for perpendicularity. So if you are not representing this MMC means, then it's a different thing. It will not vary. But the designer has decided that this component, if it is at maximum material condition, I need the perpendicularity at 0.2. So I am giving a play for the manufacturer. So manufacturer has got some perpendicularity can be slightly increased also. So he gets a perpendicularity tolerance. A wide perpendicularity tolerance is being applied. So the quality control guy can check here and he can see that if the hole is at maximum metal condition, then only it should be at 0.2. If your hole size is varying, he can relate it. He can relate the hole size with respect to the perpendicularity and he can measure it and see that if it is beyond that 0.2 also, it is accepted. So as per the feature control frame, it is 0.2, but I have produced a hole at say 4.3 millimeters and my geometric tolerance, the perpendicularity is coming say 0.4 or 0.5 or 0.3. It is accepted only. But at 4.3, if you are getting 0.6, then it is rejected. So the opposite condition, least material condition also, how it is going to play. So same, it will be in the opposite direction. For example, as per this feature control frame, what it says is the hole 4.5 to 4 mm hole should be within a 0.2 cylindrical tolerance. That is, the perpendicularity should be within 0.2 cylindrical tolerance zone when the hole is at LMC, that is least metal condition. So when the hole is at least metal condition, here the hole is 4.2 will be the least metal condition. When it is at least metal condition of 4.5, the perpendicularity tolerance should be 0.2. When it moves towards the MMC, the perpendicularity can also increase. So these are all given by the design engineer in the drawing. So as per the drawing, the quality checker can check it out and he can take a decision whether this component can be rejected or it can be accepted, even though the perpendicularity tolerance is not within 0.2. The reason is we have applied a modifier, that is L or M, that is present in this geometric tolerance zone. Regardless of feature size principle. So as I discussed earlier, in this feature control frame, there is nothing you can see after the value. That is, you have the geometric characteristic symbol and a cylindrical tolerance zone symbol is given and value also given, followed by there is no modifier. M within circle or L within circle is missing, which means there is no modifier. What it says is, regardless of your hole size, this hole can vary between 9.9 to 10.1. That is what this tolerance means. But the perpendicularity should be 0.2 at any point of your time. Like means whether your hole can be 9.9, the perpendicularity tolerance will be 0.2 only. If the hole is at 10, then also perpendicularity tolerance is 0.2. If your hole is at 10.1, then also the perpendicular tolerance will be 0.2. So the perpendicularity tolerance is always 0.2 regardless of what the size of the hole is. That is why it is called as regardless of feature size. So when you give any modifier, then only it will be applicable. If you don't give any modifier here, then what it means is whatever the size of the hole, if your size of the hole is within this only, then it's accepted. Within the tolerance only, this component will be accepted at first point. Once your hole is within the tolerance zone, then when they check for the perpendicularity, it should be within 0.2 only, whatever your size may be. So that's what it means, regardless of feature size, RFS. Now we'll see the datum reference. So in the feature control frame, we have three zones. One is the geometric characteristic zone, second was the geometric tolerance zone, and datum reference zone. So third one is the datum reference zone. So geometric characteristic zone is nothing but the geometric symbols which we are discussed in the last session, and geometric tolerance zone just now we have discussed, and datum reference. Datum reference is nothing but with reference to what datum you are telling about your geometric characteristic. So this can be applied, the datum reference can be used along with the orientation, runout, profile or location tolerance in the for PL, except F is for form. So except for the form tolerance, this datum reference can be used for the other four categories. Orientation, runout, profile or datum tolerance must be related to a datum or datum reference is used. So like whenever you need to use these tolerances, you can use a datum reference. So the conditions or principles for datum references, there can be maximum of 3 datums and they are listed in the order of importance, which means that in this case, for example, if you look into this drawing, as per the feature control frame, A, B, C is given. It can be B, A, C also. If it is A, B, C, then first one is the first important, which is called as the primary, second one is the secondary, and third one is the tertiary. If it is BAC, then your B will become the primary and A will become the secondary datum. So this is as per your drawing. So how you have created the datums in the drawing, accordingly you can keep it here. There is no need that it should be always A, B, C in the alphabetical order. It can be changed also as per our drawing design where we have selected the datums. But the first one will be the primary datum, second one will be the secondary datum, and third one will be the tertiary datum. But there is no compulsory you need to have all the 3 datums. There can be only 1 datum or 2 datum, or you can have 3 datums also. So the do's and don'ts for proper display. This is just a snapshot of all the tolerances, like the geometric tolerances, which we'll be seeing in detail in the further sessions. This will give you some idea like how the feature control frames needs to be represented in the drawing for properly, so that the reader will not get any confusion, or interpretation will be very, very easier. So under form tolerance, as we know, we have flatness, straightness, circularity and cylindricity. The common element for all these 4 is there is no datum reference. As we discussed in the previous slide, for the form tolerance, the datum reference is not at all required. And this is for the orientation tolerance, where you have the datum references mentioned in all these 3. So datum reference, you can use it for perpendicularity, angularity and the parallelism. This comes under the orientation tolerance. And second one is for the runout tolerance. Again, in runout also you can have the datum reference, total runout and circular runout. And profile tolerance, profile of a line and profile of a surface, both can have a datum reference. If required, you can give a datum reference. And for the location tolerance, same thing, position, concentricity and symmetricity. For all these 3, you will have a datum reference.